And here we are back into the second video of shaders. We ended up the first video by looking at these examples where we're manipulating the XYZs and forcing them to be turned into colors in two different ways. Let's see some of the other stuff we can do. Ooh, as promised, let's look at per fragment lighting. So if we were doing per vertex lighting, we would take the vertex, which is GL vertex, or the underbar, or GL underbar vertex, and we would use that with the vectors pointing to the light and the normal and so on, compute an intensity based on the ambient diffuse specular equation, and then send that intensity out to the rasterizer. It would be interpolated, put back in um, fragment shaders, where it would be passed into GL frag color. Okay, and the equations look like this. That is, when we want to get the cosine of the angle between the normal and the light, we do this with a dot product. And dot is a built-in function in GLSL because it comes up so often. Okay, when we want to normalize a vector, unitize a vector, whoa, there's a built-in normalize function. When we want to raise something to when we want to do the cosine of phi, we do a dot product. When we want to raise that to the shininess power, we do pow, just like in C. So the equations look pretty much like what you think they should. Now, let's go back because we're not doing per vertex lighting, we're doing per fragment lighting. So here's what we've got. We've got some out variables, okay, begin with a V. We're going to set the light position, and normally I would make this a uniform variable so that it can be changed from outside the shaders. Just for ease of reading, I've made it a constant vec3 inside the shader. If you want to do texturing, here's how you find out the S and T coordinates of the vertex that we're looking at right now. And so we're going to set it to this out variable so we can pass it over in case we need it. We're not going to use it in this case. The I coordinate position is the model view matrix times the vertex. And we're doing that so we can figure out we can figure out where the transformed point is. We're going to do the lighting after transforming the point. We need to also transform the normal. Actually, we haven't really talked about that much, but think about it. If I've got this object and here's the normal of that face, if I rotate that object, I need to rotate the normal as well. Otherwise, the lighting is going to get screwed up. So here is the matrix for transforming the normal. It basically is a variation on the model view matrix. Here is the vector from where we are, the point P in our lighting notes, to the light position. Here's where here's the I vector. It's from where we are to the I position. Now, why is 0, 0, 0 the I position? Because it is. That's what GLU look at actually does. The OpenGL hardware assumes the I is at the origin looking in negative Z. This deserves a picture. Z, X, Y, right-handed system. The OpenGL hardware expects the I to be here looking there. That's what GLU look at actually does, is it forces a transformation such that the I ends up at the origin looking in negative Z, no matter where you put the I to begin with. Okay, so that's why here we make it, the I is at 0, 0, 0, because it already has been put there. And we subtract where we were, or where the point is, and that gives us that I vector. Okay, model view projection matrix times GL vertex, pass that down the pipeline. But now we've got a whole bunch of other information, including all these vec3s. Those are the vec3s from the lighting equation, and the fact that we've made them out variables means they are going to be interpolated into the fragment shader. Here are some uniforms. They can be set from outside. This is the color of the object. This is how much specular, diffuse, and ambient there should be. And typically when we set that, we set them so they add up to 1. You can't oversaturate a color. That is, the RGB numbers only go as high as 1. If you put a bigger number in there, it'll just clamp it to 1. So we don't. Here is the specular color, which is really the light color, and here is the shininess exponent. So we're going to unitize those because we'll need to have them as unit vectors when we do the dot product. The ambient is just the color of the object times this coefficient. I typically use like 0.1 or 0.2 for Ka. Here comes the diffuse. We're going to do the dot product. Now, if that dot product turns out to be negative, it means the light is not seeing the front of the object. And so that's why we're doing this max. It basically is like an if statement. If the dot product is negative, use 0 for D. And then we're taking that D, which is the dot product, times the color of the object, times this. And oftentimes I use like 0.6, 0.7 for KD. I like a lot of diffuse. And then here comes the specular. We're going to do the reflection. Angle of reflection equals angle of incidence. There is a built-in reflect function in GLSL for exactly this reason, because you are doing reflections. We're doing the dot product to get that angle we called phi in the lighting notes. If it's negative, the light can't see the point. And then we're raising it with the pow function to the shininess power. And there's our specular. And so you add up the ambient, diffuse, and the specular, make sure your alpha is 1, poof, you're done. So per fragment lighting is not that tricky. Really, we've just moved the lighting equation from the vertex side to the fragment side. And instead of interpolating intensities, we are interpolating vectors. But the equation's the same. Yep, there it is. Ambient, diffuse, specular. Put it all together. What have you got? This. And what's fun is if you hook up the Ka, Kd, Ks into sliders or something like that, you can really adjust this. And there will be a demo video on shaders, and I'll show you that in that video. All right, drawing a pattern. You have a project 5 where, what's your assignment? Drawing a pattern on an object. So you can pick pretty much any pattern you want. It has to be a changing pattern. That is, it has to be undulating, like picking a red circle and just moving it left to right across the object. No, not good enough. It's got to be a circle where the radius changes, the position changes. We're doing shaders now. We're grown-ups now. So what if, and by showing you this, you can't use it, but what if what we wanted to do, let's say we had a sphere, and what we wanted to do was put a rectangle somewhere, and we wanted to make the rectangle red. And we wanted to be able to change the position and size of that rectangle on the fly. So maybe we do a function of time and change those things. Well, okay, so what that says to us is the center position and the sizes better be uniform variables because you want to set those from the outside. You want it to change every frame. And so that's why they begin with a lowercase u. They're uniform variables able to be set from the outside. Remember that this VST, that's a vec2 that's holding the S and T texture coordinates. So texture coordinates are really just locations on the object. We happen to most of the time look up textures with them, but we don't have to. We can just use them as identifying locations. And that's what we're doing here. Even though we're using the S and T coordinates, we are not looking up textures. We're not looking up texture images. So here's what we're saying is if the S where we are right now is greater than the left side of where we want the square to be, and if where we are right now is less than the right side, so if we're somewhere in between the left and the right, and if the t where we are right now is greater than this bottom location, and if the t where we are right now is less than the top location, use a color of red. Otherwise, use whatever the object color that was originally set was. Okay? And so this is what you would put in the top of your fragment shader, followed by all the per fragment lighting stuff we already saw. Okay? So you determine the raw color first, and then you determine how to light it second, and then you assign to frag color. And so you get something that looks like this, except, this is now changing size, dynamically animated as a function of time. The cool thing is this is procedural textures. Essentially, this is a texture, but it's not a texture looked up in an image. It's a texture looked up in an equation. And that's a procedural texture like we saw with the Oregon map, like we saw with the Mandelbrot set way, way back in the texture notes. And the cool thing is if you keep zooming in and zooming in and zooming in, you don't lose resolution, at least until you get up to like 10 to the fifth and you start losing floating point precision. But you don't lose it. So anyway, here we've zoomed in and we still have a very crisp edge on it. Okay, so this is sort of a model of what you might do in Project 5. There's got to be a pattern of some sort. It's got to change dynamically. It could be a circle, it could be an ellipse, it could be your initials, however you want to do it. Because this is really the beauty of shaders. It's sort of only limited by what you can think of to do. And really, that's where shaders came from. Once the game companies really got going with cool graphic stuff, it became miserable for the OpenGL driver writers because the game companies would show up and they'd say, oh, and we want this feature built into OpenGL and this feature built into OpenGL and make it work fast in your hardware. And at some point, the OpenGL vendors, NVIDIA, AMD, and so on, just threw up their hands and said, we can't keep up with what you're demanding. Well, what if we give you the ability to make your own code? And so, yeah, there we go. So, really the only limit is the kind of imagination you can pour into it. All right, so that's the second video on shaders. And come on back, we'll wrap it all up in the third video.